In this presentation, I'll go through some notes from Chapter 5 of the book, Designing Data-Intensive Applications. Chapter 5 is about replication. This is a nice image author has put for Chapter 5, which you can appreciate on your own time. Let's move on. Okay, so here are some highlights. Let's start with replication use cases. This chapter looked at the issue of replication. The replication can serve several purposes. High availability, that is keeping the system running even when one machine or several machines or the entire data center goes down. Disconnected operations, allowing an application to continue working when there is a network interruption. Latency, placing data geographically close to users so that users can interact with it faster. Scalability, being able to handle a higher volume of reads than a single machine could handle by performing reads on replicas. The chapter discussed three main approaches to replication. Single leader replication, where clients send all writes to a single node, the leader, which sends a stream of data change events to other replicas, that is followers. Readers or reads can be performed on any replica, but reads from followers might be stale. Then the second one is multi-leader replication. The client sends each write to one of several leader nodes, one of which can accept writes. The leader sends a stream of data change events to each other and to any follower nodes. And the third one is leaderless replication. Clients send each write to several nodes and read from several nodes in parallel in order to detect and correct nodes with stale data. We'll look at each of them in some detail in coming slides. So continuing on, replication approaches. Each approach has advantages and disadvantages. Single leader replication is popular because it is fairly easy to understand and there is no conflict resolution to worry about. Multi-leader and leaderless replications can be more robust in the presence of faulty nodes, network interruptions, and latency spikes at the cost of being harder to reason about and providing only very weak consistency guarantees. Replication can be synchronous or asynchronous, which has a profound effect on the system behavior when there is a fault. Although asynchronous replication can be fast when the system is running smoothly, it's important to figure out what happens when replication lag increases and servers fail. If a leader fails and you promote an asynchronous updated follower to the new leader, recently committed data may be lost. So that might be a durability issue. Replication lag. The chapter also looked at some strange effects that can be caused by replication lag, and they discussed a few consistency models that are helpful for deciding how an application should behave under replication lag. First one is read after write consistency. Users should always see data that they submitted themselves. Second is monotonic reads. After users have seen the data at one point in time, they shouldn't later see the data from earlier point in time. The third one is consistent prefix reads. Users should see the data in a state that makes causal sense. For example, seeing a question and its reply in the correct order. Now, let's look at some notes. The first one would be why replicate. There could be multiple reasons, but here are the three which are listed in this chapter. The first one is to keep that data geographically close to your users and thus reduce latency. The second one is to allow system to continue working even if some parts of the systems have failed and thus increase availability. And the third one is related to scalability, which means to scale out the number of machines that can serve read queries and thus increase read throughput. Leader and follower. Now, each node that stores a copy of the database is called a replica. Again, the leader and follower is being discussed in the context of databases. So here, every database that stores a copy of database is called a replica. With multiple replicas, a question inevitably arises: how do we ensure that all data ends up on all replicas? Every write to database needs to be processed by every replica. Otherwise, the replicas would no longer contain the same data. The most common solution for this is called leader-based replication, also known as active-passive or master-slave replication. One of the replicas is designated the leader, also known as a master or primary. When client wants to write to the database, they must send their request to the leader, which first writes the data to its local storage. The other replicas are known as followers. Whenever the leader writes new data to its local storage, it also sends the changed data to all of its followers as part of a replication lag or change stream. As part of a replication log or change stream. Each follower takes the log from the leader and updates its local copy of database accordingly by applying all writes in the same order as they were processed on the leader. When a client wants to read from the database, it can query either the leader or any of the followers. However, writes are only accepted on the leader. The followers are read only from the client's point of view, and this is the case for the single leader application. Now here is a little cartoon which shows leader-based replication. So as you can see from the left-hand side, the user or customer read-write queries, and the query goes like update users, set picture URL equal to me new.jpg, where user ID equal to 1234. And then there is a leader replica which accepts these writes, and then it sends a replication log stream to the follower replica. There are two followers here, so it sends to both of them. And the data change captures the table, which is users in this case, then primary key, which is 1234, and then various other columns. Like one column is picture underscore URL, old value, new value, and what is the transaction ID. And then the user 2345 views user 1234 profile, and it can read from one of the follower replicas. In the example here, the replication to follower one is synchronous. The leader waits until follower one has confirmed that it received the write before reporting success to the user and before making the write visible to other clients. The replication to follower two is asynchronous. The leader sends the message but doesn't wait for the response from the follower. So as you can see in this cartoon, the leader-based replication with one synchronous and one asynchronous follower is shown. The advantage of synchronous replication is that the follower is guaranteed to have an up-to-date copy of the data that is consistent with the leader. If the leader suddenly fails, we can be sure that the data is still available on one of the follower. The disadvantage is that the synchronous follower doesn't respond for whatever reason, because it may have crashed, or there is a network fault, or any other kind of error. The write cannot be processed. The leader must block all writes and wait till the synchronous replica is available again. Often, leader-based replication is configured to be completely asynchronous. In this case, if the leader fails and is not recoverable, any writes that have not been replicated to followers are lost. This means that a write is not guaranteed to be durable if it has been confirmed, and even if it has been confirmed to the client. However, a fully asynchronous configuration has the advantage that leader can continue processing writes even if all of its followers have fallen behind. Handling note outages. What happens if the leader fails? An automatic failover process usually consists of the following steps. Determining that the leader has failed. There are many things that could happen or that could potentially go wrong. It could be crashes, power outages, network issues, and more. There is no foolproof way of detecting what has gone wrong, so most systems simply use a timer. Nodes frequently bounce messages back and forth with each other, and if a node doesn't respond for some period of time, say 30 seconds, it is assumed to be dead. If the leader is deliberately taken down for planned maintenance, this doesn't apply. Picking a new leader. This could be done through an election process where the leader is chosen by a majority of the remaining replicas, or a new leader could be appointed by a previously elected controller node. The best candidate for leadership is usually the replica with the most up-to-date data changes from the older leader to minimize the data loss. Getting all the nodes to agree on a new leader is a consensus problem. Reconfiguring the system to use the new leader. Clients now need to send their write request to the new leader because it's a single leader replication setup. If the old leader comes back, it might still believe that it is the leader, not realizing that the other replicas have forced it to step down. The system needs to ensure that the old leader becomes a follower and recognizes the new leader. Failover issues. If asynchronous replication is used, the new leader may not have received all the writes from the old leader before it failed. If the former leader rejoins the cluster after a new leader has been chosen, what could happen to those writes? The new leader may have received conflicting writes in the meantime. The most common solution is for the old leader's unreplicated writes to be simply discarded, which may violate client stability expectations. Discarding writes is especially dangerous if other storage systems outside of the database needs to be coordinated with the database contents. In certain false scenarios, it could happen that two nodes both believe they are the leader. The situation is called split brain, and it is super dangerous. If both leaders accept writes, then there is no process for, and if there is no process for resolving conflicts, data is likely to be lost or corrupted. As a safety catch, some systems have a mechanism to shut down one node if two leaders are detected. However, if this mechanism is not carefully designed, you can end up with both nodes being shut down. What is the right amount of timeout before the leader is declared dead? A longer timeout means a longer time to recovery in the case where the leader fails. However, if the timeout is too short, there could be unnecessary failovers. For example, a temporary load spike could cause a node's response time to increase above the timeout, or a network glitch could cause delayed packets. If the system is already struggling with high load or network problems, an unnecessary failover is likely to make the situation worse, not better. Replication log implementation. There are various strategies. Let's go through them. So the four strategies are statement-based replication, write-ahead log shipping, logical log replication, and trigger-based replication. Now in statement-based replication, in the simplest case, the leader logs every write request or statement that it executes and sends that statement logs to its followers. In the write-ahead log shipping, the log is an append-only sequence of bytes containing all writes to the database. We can assume the exact same log to build a replica on another node. Besides writing the log to disk, the leader also sends it across the network to its followers. The third one is logical or row-based log replication. An alternative is to use different log formats for replication and for the storage engine, which allows the replication log to be decoupled from the storage engine internals. This kind of replication log is called a logical log to distinguish it from the storage engine's physical data representation. The fourth one is trigger-based replication. The replication approaches described so far are implemented by the database system without involving any application code. In many cases, that's what you want, but there are circumstances where more flexibility is needed. Replication lag problems. Continuing with the topic, we have reading your own writes. Many applications let the user submit some data and then view what they have submitted. This might be a record in a customer database or a comment on a discussion thread or something else of that sort. When new data is submitted, it must be sent to the leader, but when the user views the data, it can be read from a follower. This is especially appropriate if the data is frequently viewed but only occasionally written. So in this cartoon, as we can see, the user 1234 inserts into comments with the fields author, reply to message with values 1234, 55555, and sounds good. The leader accepts the write and it sends OK. And then it inserts into follower 1 and follower 2, and both are asynchronous updates. And as soon as it updates, it writes to the leader, it does a read. The read goes to follower 2 and it gets no result because, again, the follower 2 has not caught up with the changes that were done in leader. Continuing with replication lag problems, we have monotonic reads. Second example of an anomaly that can occur when reading from asynchronous followers is that it's possible for the user to see things moving backward in time. Continuing with the same example here, user 1234 wrote to the leader, it got accepted, and then a success was sent to client, and then follower and follower 2 were scheduled to get asynchronous updates. But before they got update, the follower 1 got its update first, and then the follower 2. Now in the meantime, if user 2345 does a read, then it might see different results from follower 1 and follower 2. As you can see from this cartoon, from follower 1 it sees the result, from follower 2 it doesn't see any results. So as the cartoon shows, a user first reads from a fresh replica, then from a stale replica. Time appears to go backward. To prevent this anomaly, we need monotonic reads. Now, if some partitions are replicated slower than others, an observer may see the answers before they see the question, and that brings to the third replication lag problem, which is consistent prefix reads. And that the third example of replication lag anomalies concerns violation of causality. Now, what are the solutions for replication lag? When working with an eventually consistent system, it is worth thinking about how the replication behaves if the replication lag increases to several minutes to even hours. If the answer is no problem, that's great. However, if the result is a bad experience for users, it's important to design the system to provide a stronger guarantee, such as read after write. Pretending that the replication is synchronous when in fact it is asynchronous is a recipe for problems down the line. As discussed earlier, there are ways in which an application can provide a stronger guarantee than underlying database, for example, by performing certain kinds of reads on the leader. However, dealing with these issues in application code is complex and easy to get wrong. It would be better if application developers didn't have to worry about the subtle replication issues and could just trust their database to do the right thing. This is why transactions exist. They are a way for database to provide stronger guarantees so that the application can be simpler. Now, let's jump to multi-leader replication. A natural extension of the leader-based replication model is to allow more than one node to accept writes. Replication still happens in the same way. Each node that processes a write must forward the data change to other nodes. We call this multi-leader configuration, or also master-master or active-active replication. In this setup, each leader simultaneously acts as a follower to other leaders. The use cases for multi-leader replication are, the first one is multi-data center operation. Imagine you have a database with replicas in different data centers. With a normal leader-based replication, the leader has to be one in one of the data centers, and all writes must go through that data center, which may not be what customers want, and that might lead to higher latencies. As you can see in this cartoon, the user read-write queries in one data center. On the left-hand side, it writes to a leader. The leader passes its changes to its follower in the data center 1. It also passes its replication log to data center 2. And then it goes through the conflict resolution logic, and then it gets applied to the leader. And that leader in data center 2 passes its changes to its follower. And same thing happens on the right-hand side. In data center 2, the user does read writes to its leaders and followers, and those changes get propagated to data center 1 leader and to its followers and conflict resolution logic. Now, let's compare how the single leader and multi-leader configuration fare in a multi-data center deployment. Performance. Again, there are three criteria the chapter mentions. One is performance, the second is tolerance of data center outages, and the third is tolerance of network problems. So in the performance, in a single leader configuration, every write must go over the internet to the data center with the leader. This can add significant latency to writes and might contravene the purpose of having multiple data centers in the first place. In a multi-leader configuration, every write can be processed in the local data center and is replicated asynchronously to the other data center. Thus, the inter-data center network delay is hidden from users, which means the perceived performance may be better. The second is tolerance of data center outages. In a single leader configuration, if the data center with the leader fails, failover can promote a follower in another data center to be the leader. In a multi-leader configuration, each data center can continue operating independently of the others, and a replication catches up when the failed data center comes back online. Third is tolerance of network problems. Traffic between data centers usually goes over public internet, which may be less reliable than the local network within the data center. A single leader configuration is very sensitive to problems in this data center link because writes are made synchronously over this link. A multi-leader configuration with synchronous replication can usually tolerate network problems better. A temporary network interruption does not prevent writes being processed. So, continuing with the use cases, we saw about multi-data center operation. The second is clients with offline operation, and third is collaborative editing. Now, looking a bit more deeply about the clients with offline operation, the situation in which multi-leader replication is appropriate is if you have an application that needs to continue to work while it is disconnected from the internet. For example, consider the calendar apps on your mobile phone, your laptop, or other devices. You need to be able to see your meetings, that is, make read requests and enter new meetings, make write requests at any time, regardless of whether your device currently has an internet connection or not. If you make any changes while you are offline, they need to be synced with the server and your other devices when the device is online. From an architecture point of view, This setup is essentially the same as multi-leader replication between data centers, taken to the extreme. Each device is a data center, and the network connection between them is extremely unreliable. As the rich history of broken calendar sync implementation demonstrates, multi-leader replication is a tricky thing to get right. Collaborative editing. Real-time collaborative editing applications allow several people to edit a document simultaneously. For example, Etherpad, Google Docs allow multiple people to concurrently edit a text document or spreadsheet. Handling write conflicts. The biggest problem with multi-leader replication is that write conflicts can occur, which means that the conflict resolution is required. So, for example, consider a wiki page that is simultaneously being edited by two users as shown in the cartoon here. User 1 changes the title of the page from A to B, and user 2 changes the title from A to C at the same time. Each user's changes successfully apply to the local leader. However, when the changes are asynchronously replicated, a conflict is detected. This problem does not occur in a single leader database. There are various ways of achieving convergent conflict resolution. Here are a few suggestive ones. Give each write a unique ID. It could be timestamp, random, long random number, a UUID, or a hash of the key and value. Pick the write with the highest ID as the winner and throw away other writes. If a timestamp is used, this technique is known as the last writer wins. Although this approach is popular, it is dangerously prone to data loss. The second one would be give each replica a unique ID and let writes that originated at a higher number replica always take precedence over writes that originated at lower number replica. This approach also implies data loss. Third one would be somehow merge the values together. For example, order them alphabetically and then concatenate them in previous figure. The merged title might be something like B/C. Record the conflict in an explicit data structure that preserves all information and write application code that resolves the conflict at the same time, perhaps by prompting the user. Continuing with the handling write conflicts, there could be custom conflict resolution logic, as the most appropriate way of resolving a conflict may depend on the application. Most multi-leader replication tools let you write conflict resolution logic using application code. This code may be executed on read or on write. Now, if it's called, let's see when it's executed on write. As soon as the database system detects a conflict in the log of replicated changes, it calls the conflict handler. For example, Picado allows you to write a snippet of Perl for this purpose. This handler typically cannot prompt a user. It runs in a background process. It must execute quickly. On read, when a conflict is detected, all the conflicting writes are stored. The next time the data is read, these multiple versions of the data are returned to the applications. The application may prompt the user or automatically resolve the conflict and write the results back to the database. CouchDB works this way. Here are some replication topologies. A replication topology describes the communication path along with which writes are propagated from one node to another. If you have two leaders, there is only one possible topology. Leader 1 sends all of its writes to leader 2 and vice versa. With more than two leaders, various different topologies are possible. As you can see, here there's a circular topology, star topology, and all-to-all topology. Next, let's talk about leaderless replication. The replication approaches we have discussed so far in this chapter, single leader or multi-leader replication, are based on the idea that a client sends its write request to one node and that the database systems takes care of copying that write to other replicas. A leader determines the order in which the writes should be processed, and follower apply the leader's writes in the same order. Some data storage systems take a different approach, abandoning the concept of a leader and allowing any replica to directly accept writes from clients. Some of the earliest replicated data systems were leaderless, but the idea was mostly forgotten during the era of dominance of relation databases. It once again became a fashionable architecture for databases after Amazon used it for in-house Dynamo system. And then RAC, Cassandra, and Voldemort are other open source data stores with leaderless replications model inspired by Dynamo. So this kind of database is also known as Dynamo style. In some leaderless implementation, the client directly sends its writes to several replicas, while in other, a coordinator node does this on behalf of client. However, like a leader database, the coordinator does not force a particular ordering of its writes. As we see, the difference in design has profound consequences for the way the database is used. In a leaderless configuration, failover does not exist. As we can see in this cartoon, the client with user ID 1234 sends the write to all three replicas in parallel, and two available replicas accept the write, but the unavailable replica misses it. Let's say that it's sufficient for 2 of the 3 replicas to acknowledge the write. After user 1234 has received the 2 OK responses, we consider the write to be successful. The client simply ignores the fact that one of the replica missed the write. Now, what is read, repair, and anti-entropy? Read repair. When a client makes a read from several nodes in parallel, it can detect any stale responses. This approach works well for the values that are frequently read. Anti-entropy process. In addition, some data stores have a background process that constantly looks for differences in the data between replicas and copy any missing data from one replica to another. Unlike the replication logging leader-based application, this anti-entropy process does not copy writes in any particular order, and there may be significant delay before data is copied. More generally, if there are n replicas, every write must be confirmed by W nodes to be considered successful, and we must query at least R nodes for each read. In the example we have seen so far, n was equal to 3, W was 2, and R equal to 2. So as long as the condition of W plus R greater than n applies, we expect to get an up-to-date value when reading, because at least one of the R nodes we are reading from must be up to date. Reads and writes that obey these R and W values are called quorum reads and writes. You can think of R and W as minimum number of votes required to read and write to be valid. In Dynamo-style databases, the parameters n, W, R are typically configurable. A common choice is to make the n number odd, typically 3 or 5, and to set W and R is equal to n plus 1 by 2. However, you can vary the numbers as you see fit. For example, a workload with few writes and many reads may benefit from setting n W equal to n and R equal to 1. This makes reads faster, but has the disadvantage that one of the nodes failed causes our database writes to fail. So here's the cartoon which depicts the relation W plus R greater than n, where at least one of the R replicas you read from must have seen the most successful writes. However, even with, here we are discussing the limitations of quorum consistency. Even with W plus R greater than n, there are likely to be edge cases where stale values can be returned. These depends on the implementation, but possible scenarios are following. If a sloppy quorum is used, then W writes may end up on different nodes than the R read, so there is no longer a guaranteed overlap between the R nodes and the W nodes. If 2 writes occur concurrently, it is not clear which one happened first. In this case, the only safe solution is to merge the concurrent writes. If a winner is picked based on the timestamp, that is last writer wins, writes can be lost due to clock skew. If a write happens concurrently with a read, the write may be reflected only on some of the replicas. In this case, it's undetermined whether the read returns the old or new value. If a write succeeded on some replica but failed on others, and overall succeeded on a few replicas than W replicas, it is not rolled back on replicas where it is succeeded. This means that if a write was reported as failed, subsequent reads may or may not return the value from that write. If a node carrying a new value fails, and its data is stored from a replica carrying an old value, then the number of replicas storing the new value may fall below W, breaking the quorum condition. Even if everything is working correctly, there are edge cases in which you might get unlucky with the timing. Now let's see what is sloppy quorum and hinted handoff. In a large cluster with significantly more than n nodes, it is likely that the client can connect to some database nodes during the network interruption, just not to the nodes that it needs to be to assemble a quorum for a particular value. In that case, database designers face a trade-off. Is it better to return errors on all requests for which we cannot reach a quorum of W or R nodes, or should we accept writes anyway and write them to some nodes that are reachable but aren't among the n nodes on which the value actually lives? The latter is known as a sloppy quorum. Writes and reads still require W and R successful responses, but those may include nodes that are not among the designated n home nodes for a value. By analogy, if you lock yourself out of your house, you may knock on your neighbor's doors and ask whether you may stay on their couch temporarily. Once the network interruption is fixed or the errors are fixed, any writes that the node temporarily accepted on behalf of another node are sent back to the home nodes. This is called hinted handoff. Once you find the keys to your house again, your neighbor may politely ask you to get off their couch and go home. Sloppy quorums are particularly useful for increasing write availability. For as long as W nodes are available, the database can accept writes. However, this means that even when W plus R is greater than n, you cannot be sure to read the latest value of R again, because the latest value may have been temporarily written by some of the nodes outside of n. Now, Dynamo-style databases, that is leaderless replication configurations, allow several clients to concurrently write to the same key, which means that conflicts will occur even if the strict quorums are used. The situation is similar to multi-leader replication, although in the Dynamo-style databases, conflicts can also arise during the read repair or hinted handoff. The problem is that events may arrive in a different order at different nodes due to variable network delays and partial failures. For example, in the cartoon here, it shows two clients A and B simultaneously writing to a key X in 3 nodes data center. Node 1 receives the write from A, but never receives the write from B due to a transient outage. Node 2 receives the write from A, but then write from B. Node 3 first receives the write from B and then from A. So as you can see from the image, it's showing the concurrent writes in a Dynamo-style data store, and there is no well-defined order. Now, let's talk about last writer wins or discarding concurrent writes. One approach for achieving eventual convergence is to declare that each replica need only store the most recent value and allow older values to be overwritten or discarded. Then, as long as we have some way of unambiguously determining which write is more recent and every write is eventually copied to every replica, the replicas will eventually converge to the same value. As indicated by the quotes around recent, this idea is actually quite misleading. In the previous example, neither client knew about the other one when it sent its write request to the database nodes. So it's not clear which one happened first. In fact, it doesn't really make sense to say that either happened first. We say that the writes are concurrent, so their order is undefined. Even though the writes don't have a natural ordering, we can enforce an arbitrary order on them. For example, we can attach a timestamp to each write, pick the biggest timestamp as the most recent, and discard any writes that with an earlier timestamp. This conflict resolution algorithm, called last writer wins, is the only supported conflict resolution methods in Cassandra and optional feature in RAG. Last writer wins achieves the goal of eventual convergence, but at the cost of durability. If there are several concurrent writes to the same key, even if they were all reported as successful to the client because they were written to replicas, only one of the writes will survive and others will be silently discarded. Moreover, LWW may even drop writes that are not concurrent. So, version vector. The collection of versions number from all replicas is called a version vector. Version vectors are sent from database replicas to clients where values are read and need to be sent back to the database when a value is subsequently written. The version vector allows database to distinguish between overwrites and concurrent writes. Also, like in the single replica example, the application may need to merge siblings. The version vector structure ensures that it is safe to read from one replica and subsequently write back to another replica. Doing so may result in siblings being created, so no data is lost as long as the siblings are merged correctly. A version vector is sometimes also called a vector clock, even though they are not quite the same. In brief, when comparing the state of replicas, version vectors are the right data structures to use. So this concludes chapter 5 notes. Hope this was useful. Have a nice time. Like and subscribe for more such content.